Most RAG systems do not fail because the model is weak. They fail because the FAISS index picked the wrong neighbors.
Exactly. In FAISS, an index type is the data structure and search strategy used to store vectors and retrieve nearest matches. It decides the trade-off between speed, memory, and recall.
So, this is not a boring implementation detail. This is the part that decides whether your app feels instant and smart or fast and wrong.
That is the stakes. If retrieval misses the right chunks, the model sounds confident, but answers from weaker evidence. Index choice can quietly move quality more than prop tweaks do.
Give me the practical frame. I have embeddings, I have a corpus, I need top K. Where do index types enter the story?
Right there. FAISS can search every vector exactly, or it can use shortcuts to search only promising regions or compressed representations. Those shortcuts are why one index can answer in milliseconds, while another takes much longer.
Let's make that concrete. Say I'm building internal doc search for a company, and the corpus jumps from 50,000 chunks to 5 million. What changes?
At 50,000, a flat index may be fine. At 5 million, exact search starts to hurt latency and hardware costs. Suddenly, the index type becomes a product decision, not just an engineering preference.
Start with flat, because people hear exact search and assume that must be best.
Flat means brute force nearest neighbor search. Every query compares against every stored vector. High recall, simple behavior, easy to reason about, and often the best baseline. The downside is predictable. Slower search as data grows, and memory can get expensive.
So flat is the honest worker. No tricks, but no mercy on compute either.
Perfect way to say it. If you need the highest confidence in recall, or your dataset is still modest, flat is a strong default. It is also the benchmark you should measure other indexes against.
Now the pressure point. Traffic spikes. Users want sub-second answers, and the CFO notices the GPU bill. What is the first escape hatch?
Usually, IVF, inverted file indexing. IVF partitions the vector space into clusters. At query time, FAISS first finds the most relevant clusters, then searches only inside those instead of scanning everything.
So the trick is not searching less randomly, it is searching less, but with a map.
Exactly. That can cut latency a lot, but there is a risk. If the right neighbor lives in a cluster you do not probe, recall drops. You gain speed by accepting that the search is approximate.
Give me a real RAG consequence, not a benchmark chart.
Imagine a support bot over millions of troubleshooting notes. A query about a rare firmware issue lands near a border between clusters. If IVF probes too few clusters, it may miss the one note with the real fix. The bot still answers, but now it answers from generic documents and sends the user down the wrong path.
That is the dangerous version of fast. Not failing loudly, failing smoothly.
Right. With IVF, tuning matters. More clusters can improve search focus. Probing more clusters can recover recall. But each gain pushes latency back up. You are balancing product response time against the chance of missing crucial evidence.
Where does HNSW fit? People talk about it like it is magic.
HNSW is a graph-based index. Vectors are connected in a layered small world graph, and search walks the graph toward close neighbors. High level, it often gives very strong speed and recall without scanning huge portions of the dataset.
Why does that feel so attractive for RAG teams?
Because it often lands in a sweet spot. Better recall than many loose approximate settings, much faster than flat at scale, and conceptually straightforward in use. The trade-offs are memory overhead and build complexity. It can also be slower to construct or update than simpler choices.
So, if my corpus changes every hour, that matters. If it changes once a week, maybe less.
Exactly. Think of a news monitoring system. If new articles stream in constantly, index maintenance becomes part of the architecture. A search method that looks great in static benchmarks may become painful operationally when data churn is high.
And PQ. This is the one that scares people, because compression sounds like damage.
That is the right instinct. Product quantization, or PQ, compresses vectors into compact codes, so search uses far less memory and can be much faster. The price is approximation error. You are not comparing full precision vectors anymore. You are comparing compressed versions or compressed distances.
So PQ is the survival move when the dataset is huge and memory is the real bottleneck.
Yes, think tens or hundreds of millions of chunks. Without compression, costs can become unrealistic. PQ lets you keep the system standing. But if your retrieval task depends on subtle semantic distinctions, too much compression can blur exactly the differences your model needs.
Give me one practical decision path. I am launching a RAG assistant for legal documents. Accuracy matters, but users also expect quick answers.
Start with flat on a representative sample and measure recall and latency. If flat already meets the target, stop there. If not, try HNSW for a strong speed recall balance. If the corpus is very large and memory is the pain, evaluate IVF, often with careful probe tuning, and consider IVF with PQ when compression becomes necessary. The key is to compare against flat, using your real queries, not generic nearest neighbor tests.
So the winner is not the fanciest index. It is the one that loses the least, in the way your product can least afford.
Exactly. In FAISS, index choice is strategy. Flat buys certainty. IVF buys speed through partitioning. HNSW buys speed through graph navigation. PQ buys scale through compression. Pick the wrong one, and your RAG system retrieves excuses instead of evidence.